Let me recorrect a few facts about this equation. E squared minus 1 is equal to 2 times x squared. All these are positive quantities. If E is positive, then E squared is greater than 1, E is, and that is hyperbolic. How do you see that? Let's go back and write this equation. R becomes equal to A1 minus E squared divided by 1 plus E cos theta. When if E is greater than 1, cos theta, when theta is 0 is 1, theta is 90 degrees, it is 0, and as it is going on, theta is increasing, cos becomes negative till it becomes minus 1. So this will become 1 minus E. But if E is greater than 1, this is going to become a negative number. So at some value of theta, in particular 1 by E, this denominator is going to become 0. So R goes to infinity. Right? So R goes to infinity. This is my direction. This angle, theta 0, if I call that, is cos theta 0. Is minus. Okay? And so, but on the other hand, if E is 0, E is exactly equal to 1, and that is the pattern. And if E is less than 1, that is, sorry, this is E equal to 0, this is E. So as far as Cassini is concerned, it is coming from infinite distance as far as Jupiter. So at very far away, the potential energy is 0 coming from Jupiter. It has kinetic energy, therefore E is greater than 0. Therefore it is following a hyperbolic path. And the hyperbolic path will come like this and it will bend and go in that direction. Whatever be the initial velocity with which it came, the final velocity must also be the same because energy is conserved. There is no potential energy when you are very far away from Jupiter. So the energy here is the same as the energy here. That means omega I magnitude is equal to.
What is omega?
Omega is the initial velocity with which the particle is touched.
Linear.
With respect to the Jupiter.
Linear.
But linear. Oh, because the symbol omega.
And
Yes.
why should it be same? Because we are talking Jupiter's respect.
No, R going to infinity would be, again, it will occur at theta minus theta equal to. Notice, this equation is symmetric for theta going in, theta to minus theta. So, if I interchange theta to minus theta, it should be in this direction.
In Jupiter's frame it is same.
I'm talking about that frame. I'm only in this frame right now. We will move to the other frame in a minute. Okay.
That argument, please repeat it. As far as E is greater than 0, when it is entering, before it is entering the
Okay,
Jupiter.
let's look at it purely from the influence of Jupiter. When it's far away, what is the potential energy due to Jupiter?
0.
It has kinetic energy. So, as far as the system of the satellite and the Jupiter is concerned, the total energy is greater than 0.
Yes.
And therefore, I am in this region. Right? As a two-body system of Jupiter and the Voyager, it is easy.
It is free from the influence of Jupiter.
Now I am not thinking of the influence of Sun.
Okay.
The another way of saying it is the following. See, when it is moving around Jupiter, in terms of distances from the Sun, it is hardly moving. Right? It is very, very far away from the Sun. So for all practical purposes, the effect of Sun is still to take over in a larger distance. So the movement we are considering is only some 10 times or 20 times the diameter of the Jupiter at the distance of Jupiter, which is very far away from the Sun. So for all practical purposes, that motion is not being influenced by the Sun.
Not wrong.
That's not wrong. Okay? That's the approximation. Of course, one can do better, but the main point we will make here. So this is theta 0, and similarly, that is also fixed. Now, I want to find out this angle. This is the angle with which it came, and this is the angle with which it bent, and this angle I call beta. So now, let's find out what is beta. If this is theta 0, this is pi minus beta. So, notice beta plus 2 pi minus beta 0, that is this angle. Here, 2 pi minus theta 0 equal to. So, beta is 2 beta 0. And theta 0 is 2 cos inverse of minus 1. So from here, I can write as cos of inverse minus inverse equal to beta pi by 2 minus 1 so what's the beta pi by 2 and that is or epsilon 1 1. Okay. Now I am all set to describe how the planet can be used for the Voyager or Cassini to gain energy from the planet. Now I look at this entire motion from the point of view of the Sun being at rest and the planet having a velocity v. So if the planet is moving in this direction, I am going to draw planet moving in that direction. I am not going to draw the planet, but I will draw the other ones. My velocity vi as it is approaching the planet is like that. Velocity of the rocket or velocity of the spacecraft in the rest frame of Sun. This is Sun's rest frame. Now, this is the velocity of the spacecraft in the rest frame of the planet. How do I get that? I draw, and let me make this a little bigger. I draw minus v, the velocity of the planet. And this will be my omega. Yes.
Subtle point which I think
Yes, please.
teachers in the audience should do numerical calculations and get order of magnitude. Strictly speaking, the frame of reference in which Jupiter is at rest is not an inertial frame.
That's also right.
It is inertial to a very good accuracy, but better inertial frame is the one at rest with respect to the Sun.
Yes.
Just as a frame based on the Earth but not rotating is not a good inertial frame because of the Earth's motion around the Sun. So it's useful to calculate to what degree it is not a inertial. Some numerical estimate.
By the way, supposing I wanted to actually calculate what are the steps that we need to do is the question. The question is, suppose, let's talk about the Earth going around. We treat normally Earth as an inertial frame, but it is not an inertial frame. So the reason for that is the acceleration of the Earth going around the Sun. So if I want to treat Earth as an inertial frame, I will have to introduce what is called a pseudo force. And the pseudo force is essentially Hubble force. It is going away from the Sun. And you can calculate the magnitude of that force on 1 kilogram per meter. And that's nothing but mg squared by r, assuming the circular motion for it. And that you will be able to find out.
Earth it is 10 raised to minus.
Pardon?
For Earth it will be 10 raised to minus 18.
Is that right? I do it so maybe. I will check that.
Minus 18.
Minus 18 you said.
1 8.
1 8. Is it 30 kilometers per hour is the speed of the Earth.
Per second.
Per second. Sorry, per second.
That gives you 9 10 raised to 4.
Okay.
And
150 million.
Yeah. So that is 1.5 into 11.
Ah.
Oh, okay, 11. Not square.
Okay. Alright, that's it.
That is to minus 7.
Some number like that is fine. So for Jupiter it's even smaller because it's V is smaller and R is larger. Okay. So I am the Sun's restraint as Buddha says this is a better initiative. He used the word better. So why?
25 times.
Oh, it is the Sun is also going around the galaxy. So there is a galaxy going around. So you don't worry about that if you want to take care of that. In fact, the statement of Newton's first law is the statement of the existence of an inertial frame. That there exists an inertial frame. Maybe in nature there is nothing called an inertial frame. So that's the assumption. Okay. Now, so this is my omega r. I do the same thing for my omega n. So I draw my VF vector like that. And actually omega f I have to draw like that. So omega, the omega f, this will be my, I will write this as omega I and omega f. I'm writing it like this, but so Vf is this and omega f is this. And this angle is given. Let me give some symbols to this. C prime, B prime is perpendicular, and then I have this point A. And let me write down some expressions. Angle BOA alpha. Instead of trumping the diagram, I'll try to keep it like this. Angle C, no, it's not that. This is P. Then this is CPA. This angle prime. I have PA is B and OB is Now I have to do some simple trigonometry at this stage. Notice omega f is equal to omega I, and I am just going to call that omega. Omega sine beta plus gamma. So what is gamma? Gamma is that angle. I'll also write that down. The angle CA C prime. Omega beta plus gamma sine notice this is omega BB prime BB prime is BB prime is beta plus omega sine beta plus gamma, and that must be equal to VI sine. Similarly, omega sine gamma is equal to VF sine.
What is omega here?
Pardon?
Omega.
Say it again, please.
Omega is
Omega is AB. Length omega is AB, also equal to AC. Right? Let me repeat the situation. Notice this is the rest frame of the planet. In the rest frame of the planet, it comes with omega and goes with omega in different directions. In a velocity, speed is the same. Now, here it is coming with Pi and it is leaving with Ps. Okay? Now, I draw my Vi here and Vf in this direction. Minus P I have to subtract to get to the planet's frame. So, in the planet frame, it is coming with omega I and it is leaving with omega L. Okay? But magnitude of omega I is the same as the magnitude of omega L. So, that's why length AB is equal to AC is equal to omega. Correct? Now, similarly, what is OB, PB prime? PB prime from here to here is PB prime is VI cos alpha. That's also equal to this plus that. That's equal to V plus omega cos beta. Similarly, PC prime is Vf cos alpha prime. PC prime is this distance is Vf. This is the crucial equation for it.
Have you implicitly assumed the Sun, the Earth, Jupiter, and the
All the same. All the same. That also I shall mention today. All of them are same. It's a two-dimensional. following test. I send in my spacecraft which is on the velocity Vr. I in the sun spec, I want the velocity Vf to go. Right? It's coming and meeting with the planet, and when it leaves, its velocity should increase compared to this planet. So, what are my input parameters which I am going to fix? I am going to take Vi alpha, the angle of approach to Jupiter or to the planet. This angle is alpha. So this is the direction of the motion of planet, and this is the direction of approach. Okay, alpha, and V, of course, the velocity of the planet, which is fixed. Okay. And what am I going to vary? I am going to vary the approach, how close should it get to Jupiter. That is, therefore, if it gets very far away, it will not get deflected. If it gets very close, it will get deflected a lot. So, the parameter that I am going to vary, V is my parameter. And notice, where is that expression? Here it is. Beta is related to epsilon. So ultimately, if I know beta, I will know epsilon, and once I know epsilon, I know what should be the trajectory. Right? That will be the strategy. So given this, all I need to do is calculate d Vf squared by d beta and see what it gives me. When I do the calculation, I will again skip steps and write down the answer. It gives me tan beta equal to Vi by d sin divided by Vi.
Delta Vx square, sir?
Pardon?
Is it delta Vx square by delta beta? A derivative that is 0, that is dV square.
dV, whether it is dV squared 0 or dV 0, it doesn't matter. Because if Vf is a maximum at a place for some value, Vf square is also maximum. And then I will also write down that expression. This expression I want to rewrite. I need it. I will rewrite it. So now I am going to take some specific values and plot it. If I take V, the velocity of the planet as my unit, I can write down here a ratio which is Vf by Vi whole square divided by V whole square divided by. This is the ratio essentially of Vf squared by Vi squared. The final speed by which the spacecraft is coming out to the initial speed it entered. And I am going to choose my initial velocity Vi by V to be 1.5. Incidentally, Jupiter for Jupiter is 13 kilometers per second. And I am going to choose the way it is approaching alpha to be 40 degrees. Just as a numerical. And here I am plotting it as a function of beta. Notice, if beta is 0, this term is 0, so beta equal to 0, and we get R equal to 1. And that makes sense. Beta is 0 means it is going straight. It means nothing is happening to it. Jupiter is doing nothing to it. So it is going straight. Now, if you plot it, the maximum for this occurs at 81 degrees. If you substitute all that here, this comes to 81 degrees. Yes.
Step way B, equation number T. It is
Yeah.
cos beta last term. Cos alpha minus beta minus
Cos beta.
This expression,
Next one.
next term is Vx squared is Vi. I take these things and just work my way through. Do the algebra. I have skipped algebra from here to here. Vi squared plus 2V squared times 1 minus cos beta plus 2V times Vi cos alpha minus beta.
Cos beta.
Yes.
There also it should be cos beta. Yes, just again V square.
Cos beta.
Then this must not work.
Yeah, cos alpha.
Cos alpha is correct. Because when I put beta equal to 0, it should work. Yes, it is possible. So, for beta max, R is about 1.2. So the curve is actually symmetric about this. And this is 81 degrees. Now, suppose I want R to be 1.2. Let R be 1.2. I say 20% increase in velocity is adequate for me to get further wherever I want to go. And that will come to, I will draw it. R equal to 1.2. And that corresponds to two angles. Beta equal to 33 degrees and 20. It comes to 1. Notice it is completely symmetrical with respect to 81 degrees. It's 48 here, 48 this side. Okay. Now, suppose the Jupiter is here. I go back and find out what is my H. X, remember, was J by M, is the angular momentum of that. So if B is the here, the perpendicular distance from the center of Jupiter to the initial vector, JH would be B omega. Right? Because if it's coming from far away, what is the angular momentum? It is the perpendicular distance B times omega, so it is B omega per unit mass, J by N. So BH would be B omega. And what is the energy? Energy would be half m. Okay. So when I substitute all that, my b squared minus 1 to be b squared omega 4. Half will cancel, m will cancel, omega 4 by g squared. But my E is sine beta by 2 for this. Right? Yeah, please ask.
So H is equal to B omega.
How did I get B omega? What is H? H was angular momentum per unit mass. Now, let's look at it from the planet space. This is all in the planet space. It is coming with a velocity omega. And B is the perpendicular distance of that velocity vector to the center of Jupiter or the planet. So B into omega would be the angular velocity per unit mass. So that's my H is equal to B omega. Okay? But this is 1 by sine squared beta by 2 minus 1. So
this is epsilon or this is E?
please say it again. Epsilon is same as E. My notation is bad. I should have. I've been using two different things. How many places have I used epsilon? E. Okay, anyway, E. Given this, now beta I have already got. Beta was either 33 degrees or 129. So given beta, I can omega I can find out because I know what that is. Let me also write that down. So omega can be calculated from somewhere here. How can I calculate omega? Some help? From this expression. Where can I get my value?
VI sin alpha. 1 sin beta plus.
Beta is there's also one more place where omega can be calculated, and let me write down. I have the expression for omega also. Omega squared is vi squared plus v squared minus 2 vi cos alpha. This must come from one of those equations.
Cosine rule for this triangle.
Pardon?
Cosine rule for the triangle.
It will just come from this and this and this. This triangle. Okay? Omega squared is vi squared plus v squared plus 10. And if I calculate omega, the value of omega works out to be 0.9. So I know this. C for Jupiter I know. So I can calculate from here my so B, so beta equal to 33 degrees, B is, I am taking R to be 1.2. Notice, my R has been fixed to 1.2. B is 2.7 times 10 to the 6. The other alternative is beta is 129. I think beta to be 129. B is 9 into 10 to the 4 kilometers. And radius of Jupiter, all this is for Jupiter, is 7 into 10 to the 4.
Sir, that beta 33, how do you take that?
I arbitrarily chose that let me get a 20% increase in the velocity. So I am working with R equal to 1.2. Notice this expression ratio. Okay? For R equal to 1.2. If R were 1.3, I would have beta equal to 81 degrees. Is it okay? Now it's a question of choice of what value of R I want. I just took R equal to 1.2. Then I get a 20% increase.
20% increase in energy.
No, 20% increase in kinetic energy, not in cost. Pf squared by dx. Absolutely. So I want to spend 5 more minutes on what is actually going on. Firstly, these are the two angles. Here, since the radius of Jupiter is 70,000 kilometers, the closest thing is 9 10 to the 4. This is a little too close. I mean, your calculations. It's much better to fire it at with V equal to 10 to the 6. So V equal to 33 would be a better choice than, even though you are getting 20% increase in energy.
It is approaching very near to Jupiter.
Pardon?
It is approaching very near to Jupiter, the 129-degree approach.
Now this one is too close to Jupiter. This is the radius of Jupiter.
Is there any possibility of crashing here?
If you do this, then, by the way, I only calculated B. I have not calculated the closest approach it will come. That can be again calculated by using angular momentum. I have done that in my notebook, and that values I can write down. So, for this, obviously, it is, for this case, the closest approach is much less than this one. So, this is safer orbit than this orbit.
There is another problem. If you want spacecraft to go further, then that is the only approach.
Why?
Because here it will come back.
No, but that will depend upon where are you in the solar system, at what time are you doing this?
Because
Now,
in this case we are sending probe which is going outward, so naturally it becomes that.
Okay, there is a very simple physical way to understand this. Think of a collision between, this you can treat as a collision. I mean, there is, the planet is coming, the spacecraft is coming, and it is colliding with the planet and it is going in some direction. That's the way we can do it. Now think of the entire thing, and Jupiter is very heavy, the spacecraft is very light compared to Jupiter. Now think of a truck moving with some velocity v, and I throw a tennis ball at the truck. If I am in the truck frame, for all practical purposes, the truck is having infinite mass, so the ball with a velocity v when it comes will bounce back with a velocity v. But in my frame, when the truck is moving, the velocity of the ball will be much more. It will pick up energy from the truck. That's exactly what is happening in this case. What is happening? Suppose the planet is moving in this direction. It is approaching it from behind. So, in this case, the force is in this direction. So, whenever it is moving, there is a force in this direction, which is giving it that way, from the planet's point of view. So, what is happening is, when I am looking at it from here, this is approaching it this way, it means the distance is decreasing. For me, it looks like it is coming like this, and its velocity is going that way. So, the increase is because of the fact that Jupiter is pulling in, but ultimately, if I am looking at it from the Earth's frame, the sun's frame is getting a kick, and the whole system is moving. So it is essentially the same as a truck ball collision, which gives energy to the ball. Here, it is the spacecraft which is picking up energy, and Jupiter being very heavy, it will not notice any such change. So that's the essential.
Can be written in this way also.